Yeah, good afternoon. So let's start. We continue our discussion of Hoffman encoding first. All right. Then I think we'll have time to discuss another very important grid algorithm, namely texture algorithm for computing shortest paths. All right. So let's continue our discussion on Hoffman encoding first. So on Monday, we've discussed an example of how it works, and I explained the idea of how it works. And today we'll basically show its correctness. All right, because it's not obvious at all why it works. So we'll prove that it indeed works correctly. So what the algorithm does is it starts with two characters with minimum frequency and merges them to form another character. So, so this will be carried out, of course, n minus 1 times. All right. So each time we pick up two characters with minimum frequency, so these two, and replace them by a new character whose frequency equal the sum of these two characters. So then the problem is reduced to one character less. So C is updated. We replace X, Y. So we replace these two characters by this new character. All right. So that's what we do. And for these two characters, X and Y, what it happens is in the code tree, we make them siblings. So they become children of a new character C. So that's what happens. All right. So the frequency of X equals say 5, Y equals 10, frequency of Z is 15. All right. So frequency is the number of occurrence of the characters. Sometimes we normalize it. If we normalize it, then the total sum will be 1. Otherwise, if we do not normalize it, then it's a total number of characters. So that's the length of the original text. All right. So eventually, we'll return the root as a code tree. So that's how it works. All right. Is it clear how it works? But it's really not clear at all why it does compute an optimal prefix code. It's not clear at all. So we're going to prove it. Indeed, it works. I will give you proof of two important lemmas, but the final, the proof using induction for the algorithm part, I will not get into detail. It's a really trivial application of these two lemmas. So it's implied by these two lemmas, quite straightforward. But there are some tedious algebraic manipulations, which I will not discuss. You can take a look of notes. Full detail are in the notes, all right? So before I prove it, let me run an example one more time to see how it works. So suppose we have, say, A, B, C, D, E, maybe, okay. Say 5 characters. So number of occurrence may be 5 for A, say 3 for B, 6 for C, say 2 for D, and say 7 for E. All right. So what algorithm works is find the two characters with minimum frequency first. So in this case, it will be B and D. So in the tree, what happens? We have B and D, say, become children of a new character. So it's C. Okay. Actually, name does not matter. So it's 3, 2 here. So frequency of Z will be 5. All right. Now among form characters, now we deal with form characters, namely A, C, E, C. So B and D are replaced already by C. All right. Then among these, we pick 2 characters of minimum frequency. So in this case, will be 5 and 5. So C will be merged with A. So actually, this one is not important. Okay. The actual name does not matter. So it's 5 here. So this one is 5. So new character here, it's 10. All right. Now only 3 characters left. This one with 10 and the C and the E. Only 3 left. Order does not matter. The encoding may be different. Some maybe 0, maybe 1, but the length in terms of encoding is not unique because we can say A, we can use 0 for A, and maybe B it's 1 for B, but we can also use 1 for A and B for 0 for B. It's not unique. Ordering does not matter. Whether it's left or right children, it does not matter. A left or right child, it does not matter. Okay. So only 3 left. CE, CE, and this new character. C 6 7. So what happens is we merge 6 and 7. So these two will be merged into one. Let's see. I should draw it a little bit lower. It's too high. Okay. 6, 7. Sorry. E, C, and E. E. 1 is 6, 1 is 7. So they merged into one. So here is 13. So finally, these two will be merged. So it's 23. All right. So this tree will give us prefix code, which is optimal. So we can mark it edges by 0 on left side and right side by 1. So any right child will be 1, left child will be 0. So that will give us code words for these 5 characters. So namely, B will get 0, 0, D 0, 0, 1, A is 0, 1, here 1, 0, and 1, 1. All right. So we can interchange 0 and 1 so we can get different code word. But the cost or the total size will be same. Okay, the length will be same. Okay. All right, so that's how it works. Now, before we go further, what's the cost of the code tree? Just code tree. Let's say code tree, maybe. So what's the cost of this code? Cost means the length of encoding of the final code. Okay, code word. How do we compute it? All right. So it's very simple. So it's just summation. For each character, we have its distance. The character, we have its frequency times the length of encoding. So what's the length of code word? Length of code word is distance in the tree. So that's tree T. So number of edges, distance. So summation of our characters. So that's the cost. So that's the length of encoded file. All right. We need this one in order to prove the algorithm works correctly. So for example, for code for B, the length is 3. So it's occur 3 times. So it's B is 3 times 3. So that's the total length for B. For 5, it's 5 times 2. So it's summation of all these things. All right. It's also a summation of weight of internal nodes. Summation of these things is same as the cost. In actually the root, sum of the root, weight of root equal sum of frequency of leaves. I leave the detail for you to figure it out. Okay, sum of the internal nodes, weight sum of internal nodes equals this one, equals exactly this one. All right. And not sum of all nodes. That's overcounted because leaf will be added twice. Okay, but we don't really need it in our proof. So how can we prove that our algorithm indeed works correctly? So what happens is the key step is really we merge 2 characters into 1. And these 2 are of minimum frequency. Why can we do this? So really we need to show that this one always leads to an optimal code tree. If it works, all right. So let's see, in order to prove this one, what we do is to prove 2 lemmas. Actually, 1 lemma, but for this lemma, we need another one. So what we do is prove 2 lemmas. The most important thing is this one, claim, or maybe put lemma, the same thing. Okay, maybe lemma instead of claim to illustrate its importance. So that's called exchange property. As we have seen it many times, exchange property is the most important properties that enable us to design grid algorithm. Most grid algorithm based on this property. Without this property, grid algorithm will not work correctly. So what we mean by exchange property here is the following. Suppose we have two characters, x and y. All right. So suppose the frequency of x is no more than the frequency of y. And the T code tree where the code word for x is no more than the code word of y. All right. So that's assumption. So in the code tree T, so that's x, y is lower, somewhere it's lower. So that's the second property, this one. All right. Now what happens is we can change x with y to get a code tree that's no worse than t. It may not necessarily be better because it may be same. Look, here is not inequality, it's less than or equal. So after change, we'll show that the new tree will not perform worse than t. So it's at least as good as t. All right. So what happens is if we exchange x with y, so we get a new code tree. All right, so we exchange x with y. So what happens is we get a new code tree. Other things we do not change, just only x, y. So that's t, then this one is t prime. So what we can say is then the cost of new code tree is no worse than cost of old code tree. Okay. So that means a character with smaller frequency can be always put as deep as possible. So x move. So what happens is small one move downwards. So move this x down. So to this place, All right. So this one. So we'll prove that this one is very simple. Actually, it's a simple manipulation of algebra. All right. So let's prove it. So proof actually is very simple. Oh, L is a cost. So see length of encoded file as I showed you before. Let's see, where is it? Yes, this one definition is here. So here definition of L of t. All right. Okay. So let's prove why this one works. Actually, prove a very simple manipulation of algebra. Idea and so intuitively, it's easy to see once we move x down. So the cost of total cost for x is increased, but total cost of y will be reduced. But the frequency of x is smaller than y and no more than y, so total cost will not be increased. All right. So what we need to show is we just show this one. The cost of old code tree minus the cost of new code tree is non-negative. So that means the cost of new one is no more than the cost of old one. All right. So that's very simple manipulation of algebra. So just use the formula. So by definition, C in the cost distance in the old tree. So here so C is a character of C of cost minus then the cost in the new tree. So here, let me have some space here. Okay. So here, distance in the new tree, T prime. All right. So all other nodes, distance and frequency is same except X and Y. So the only difference is this term. Only this term is different. These two terms are different. Tx and ty. Sorry, dtx and dty. These two are different. All other same. All right. So this one, dt prime x equal dty, and dt prime y equal dtx. So here it's replaced. All right. So that's the only thing. So that can be easily simplified to the following. So equals fx minus fy times dtx minus dty by the assumption, these two assumptions. So this one is non-negative. All right, so we clearly have this one. So this implies indeed we can obtain a better code tree. Okay, strictly speaking, the code tree is no worse than previous one. You see here, the proof of this lemma is really straightforward, but it's a kind of tedious. It's a kind of boring, okay? So the final proof is a kind of boring, so I will not go over it. It's in the notes. All right, so this one is very important, the key property, exchange property. Now, once we have this key property, then we can use it to show that our operation indeed works. Then we are going to show that this operation indeed works. So we can always do this, x, y. So these two are minimum frequency. So exchange property allow us to show that this one always works. Okay, so that's the next property we're going to discuss. But once this one too, then it's straightforward to use induction to prove that how algorithm works. All right, okay. Okay, so lemma 2. So in the algorithm, what we have done is make these characters x, y as siblings. So that's what happened in the algorithm. So x, y will be replaced by this new character. All right. So we'll show that always optimal code tree with this structure. So therefore, it works. Okay. So this one actually is straightforward. What happens is suppose, let's see. Suppose, so without loss of generality, we may assume that x is lower than y, no higher than y. So maybe we assume this one. So in the tree, so x is lower. Y may be higher, somewhere higher. Okay. So we have this situation. All right. Now, remember this the code tree, optimal code tree is full binary tree. It's a full binary tree. So X has a sibling Z. So every internal vertex or node has degree 2. So X has a sibling Z. All right. So we have this situation. So what happens is then we see that the frequency of Z is at least frequency of Y, because the assumption is Xy of minimum frequency. All right. Now, for frequency, for the distance of Y and Z, dty is less than dtc. So we use this one and apply lemma 1 to this one using exchange property. So what we do is exchange Y and X. Oh, sorry, Y and Z. So we exchange this. Instead of putting this way, what happens is Z will be changed to Y and Y will be changed to Z. So that's new code tree T. So by the exchange property, lemma 1, we know the cost of new one. So this one is no more than cost of the old one. So therefore, we have an optimal code tree such that X and Y are indeed siblings. All right. So that's how we prove this property. Now with this property, then we'll be easily use induction to prove the whole algorithm works. It's very easy to show by induction. Here, each time number of characters is reduced by 1. So it's very natural to use induction on number of iterations, n-1 iterations. All right. So is that clear? So the most important thing actually is lemma 1. The exchange property is the exchange property. That's a key point, exchange property. With this exchange property, it follows that we can indeed make two characters of minimum frequency siblings. So putting them together, then we can use induction to show the algorithm works. All right. Now, in terms of implementation of this Hoffman code, again, as usual, greedy algorithm is very efficient, and we can easily implement it in n log n time by use priority queue of say heap, binary heap. I use function value as key. So this one as key. It's very, very easy. So each time what we need is to find two elements of minimum value from the heap. So two elements with the minimum value. So, and then the elements in the heap need to be updated because we replace two minimum elements by a new element. Updating also takes log n time. So each step takes log n time. Total time is n log n. It's very fast. All right. Okay. All right. I think that will wrap up our discussion of Hoffman code. And it's really very useful in practice and very important Hoffman encoding algorithm. I hope you can remember this one. Homework, there are one problem dealing with Hoffman encoding. All right. So any question about Hoffman encoding? Okay. All right, so it's clear, okay? All right, now we'll discuss a very important algorithm. It's really very, very fundamental, very, very important problem called shortest path. In general, now it's on weighted graph. So that's very general. A few weeks ago, we discussed shortest path for undirected graph. For unweighted graphs, use BFS. Now we want to discuss general problem, shortest path for a general weighted graph. So graph G now will be always a weighted graph. Vertex set, edge set, and weight. So weight is a function for edges. Say for simplicity, we consider just integer as weight. All right. So in general, integer as weight. So graph is a digraph in general. So here, when we say graph, we mean digraph. It also works for undirected graph. But for paths, typically we discuss it for digraphs. So we have this kind of situation. Maybe 1, 2, 3, 2, 5. All right. So our task Sorry. So we specify a particular vertex as a source, maybe this one. So we want to compute shortest path from this vertex to all other vertices. So for that particular one, we have maybe this situation. So what we get actually is shortest path tree. So that's a tree from from S, where each unique path in the tree corresponding to a shortest path. So this one, red waved one, is the shortest path tree. All right. Okay. So typically for a path, given a path P, we use LP to denote the length of P. Or sometimes we can also write W of P, for example. That's sum of weight. So this one is sum of weight of all edges on the path P. All right. Of course, then we can define distance from two vertices. Distance, that's the length of a shortest UV path between two vertices. So length of dV and the length, the distance from U to V and distance from V to U may be different. So for example, so here U, here V, 1, 3, 2. So then DUV equal 4, but DVU equal 2. For digraph, it can be different. But for undirected graph, it will be same. All right, so there one such difference between directed graph and undirected graph. Okay, so here S is a given source, and for simplicity, SU, maybe I use V. Okay, we will be written as just DV as shorthand. So that's shorthand. All right. Okay. So problem we consider is called the single source shortest path problem. A single source shortest path. So this one is called single source. So the problem we are going to discuss is this one, the single source one. Okay. So starting from one vertex. There are another version called all pair shortest path problem. So it contains this one as special case. I thought this one as fundamental subroutine. We need this one basically. So that's the most fundamental problem for computing paths. Or maybe you may ask, the most fundamental one may be given two vertices. Find, maybe given U and V, find the shortest UV path. Shortest UV path. This appears to be most fundamental one, right? But it seems we don't know how to do better for a single pair shortest path problem. Basically, to do the single pair one, we need a single source shortest path. We don't know how to do better. So it's only a single pair. So actually, in order to compute shortest path between two vertices, in the worst case, we need to compute a single source shortest path from U in the worst case. Of course, for single pair, we can terminate earlier once we reach vertex V. But in the worst case, we may need to just do shortest path from U to every other vertices. It may happen. All right. Now, how can we compute the shortest path? I think usually a shortest path algorithm will be taught in data structure course. So some of you may have learned it, but some of you may not, because last year, actually last year or the year before, because interruption of classes, these things were not taught in the data structure. All right. But anyway, I start from basically from scratch. Okay. So the algorithm we are going to discuss is the most important one, called the Dijkstra algorithm. Okay, so the spelling looks a little bit strange. The pronunciation is Dijkstra algorithm. J is not pronounced. Okay, Dijkstra algorithm. Dijkstra algorithm. Okay. So how can we compute shortest path from vertex to all other vertices? The idea actually is an extension of BFS. That's a basic idea, BFS. When the graph is unweighted, what we do is from a vertex, we visit all its neighbors. So that will give us vertices of distance 1. Then from this one, we go to next layers. So that will give us vertices of distance 2. That's BFS. So when the graph is unweighted. All right. But unfortunately now, it's much more general. Graphs have different weights. So we cannot do it in this way because edge weights are different. All right. So, but we can still use this idea and then try to simulate this idea by BFS. Actually, that's what happens. It's a simulation of BFS. So suppose we start with this vertex S. All right. All right, so that edge going out. So if some edge are unweighted, then we'll visit these 3 vertices at the same time because distance 1. Now edge is weighted. So maybe let's put this one maybe 3, this one maybe 4, this one looks like 6. All right. So what we'll do, actually we use the idea of BFS. What we can do is transform this weighted graph into an unweighted graph. So 3 means we insert 2 vertices, 4 we insert 3 vertices, and 6 we insert 5 vertices. All right, we can do it in this way. Now the graph becomes an unweighted graph. Now, of course, here it's important that edge weights is positive, right? If it's negative, how can we do that? Actually, you may ask, why do we need negative weights? It's kind of strange, right? Edge weights, of course, is positive. Later on, we'll see actually there are applications we need to deal with negative weight. It's come very naturally. All right. So we can do it in this way. And then from weighted graph, we can get an unweighted graph. Then, of course, we can use BFS. So we solve the problem. Okay, so very easy. Okay. Now the problem is the weight. The problem is really weight. So if this weight is 10, 10. You see the problem, right? Or it can be very bad, maybe 10 to power of n. So the algorithm is not even polynomial. We cannot solve it in polynomial after replacement because number of nodes is exponential. So we cannot do it in this way, just by simply replacing it in this way. But we can use the idea. The idea is as follows. So actually, there are not much point to replace an edge by its weight. Rather, if we look at this graph again, let me redraw it. So here 3. 4, here 6. So we use the idea of BFS. BFS, each time we make one step, we walk one step. So here we can also use the same idea, walk one step. So in BFS, it's 1 unit. But here we can also do one step, but rather as 1 unit. So we take the minimum of these 3. So here maybe one step is 3 units in this particular case. All right, so we rarely walk 3 units. So that's what happens. So these are distance 3. So here is 3, here is 3. So we do BFS in this way. So that's the first layer. All right, so that's first layer. Then we carry on. From this layout, we take certain steps. So maybe here 3, then next step will be 1, and so on. So that's how we simulate BFS. So that's exactly what Dijkstra algorithm works. It simulates this idea. Each time the step, we determine how much we should take in this step, how much units we take for this step. All right. So what happens is as follows. So at any time we have a tree. Maybe let me draw maybe in this way. Okay. So let S sit in the middle. So anytime we have a tree, so this tree contains visited vertices. All right, so this tree T. So that's a shortest path tree. So S visited vertices. All right. So that's for my shortest path tree. So for all vertices inside, so for these vertices, we have a computed shortest path from S to Z vertices. Now, what should be the next vertex we visit in terms of the distance? Oh. All right, so what's next vertex to visit? So there are frontier edges from this T. So there are frontier edges. Okay, so let me draw a couple of them. So which vertex should we visit? So each has a weight. Each has a weight. Maybe here's this one. So this weight 1. This one may be 2. This one may be 3. This one may be also 2. So among these 4 vertices, A, B, C, D, which one should we visit next? So here importance is which vertex to choose is determined by the distance. All right. So I get the answer A, minimum weight. All right. So I think we should include this one, this next vertex. All right. Unfortunately, what this one gives us is minimum spanning tree. So we use blue rule, we'll put A in. So that's actually minimum spanning tree. All right. But good guess. Yes, that makes sense. So the reason we cannot choose this one is because, so if I add other weights, so maybe here is 10, here is 3. But here, this one is 6. So if you look at the distance from S to A, So distance from S to A is 14. Now, if we look at distance, the others do not really matter. So maybe I add something in. Okay, maybe 1. Okay, but distance from S to D is only 8. So let me highlight it. 8. Here is 14. So the problem it may cause is actually there can be an edge outside leads from D to A. So DA or path. Maybe here the weight is 3. All right. So instead of visiting A using this path, actually a short one is from S to this one, then to D, then to A. So we cannot put A in. If we put A in, it cannot work. So this greedy method does not work. We mean to do backtracking, but backtracking is not good for greedy. All right. So what happens is we cannot just determine the next vertex to be visited depending on the edge weight for the volunteer edge. So this idea does not work. So of course you said D then, right? So but why D? So it's really determined by distance. So what we do is for each vertex, we put a distance upper bound called delta V. All right. So then next vertex we choose is vertex V with minimum distance upper bound. So that's the only thing that is different from minimum spanning tree. Instead of choosing one vertex, whose volunteer edge is of minimum weight, we choose a vertex with minimum distance upper bound. All right. Of course, this distance upper bound cannot be defined arbitrarily. It needs to be defined in a careful way. And I think time is up, and we'll continue on Monday, next coming Monday. All right. So then we'll come up, eventually we'll come up with different algorithm, and I'll show you why it works correctly. A textbook does not have correctness proof, but I think it's important to explain why it works. Actually, you will see it's really, very important. We have to prove it works because it's subtle. It's not obvious at all. All right. So I think I should stop here. By the way, no midterm exam because the COVID-19 situation is still not good. And for the final exam, I think you received the email from IES, right? It will be first face-to-face if it's possible. Of course, I fully understand some students are not in Hong Kong. And if you're not in Hong Kong, I think you're allowed to do online exam. So both ways, all right? Okay. Okay, so that's it for today. Any questions? Yes, that's a good question. Actually, homework, I will ask you to do that exercise, where the shortest path tree are minimum spanning tree, okay? Where the minimum spanning tree is shortest path tree, both ways. Maybe in the next homework, I will put it in, all right, to really understand difference between shortest path tree and minimum spanning tree. Very good question. Okay. Oh, no, for the next one. Okay, and not for homework 2. We'll be in homework 3. Homework 2 is there already. Okay, you have 1 more week, about 1 more week. All right, I think we should leave, and there are next tutorial coming up, discussion solution of homework 1. All right, bye-bye. So I'll just leave. If you want to attend the tutorial, you can just leave. Bye-bye. Sorry, you can just stay, not just leave.